So we're now going to apply this to what can happen with some very specific stories where you're actually dealing with the academic paper itself. So you can, if you've just got the press release about a paper that has been published, you can always get hold of it by basically talking to the press office. Say, can you send me a PDF of the paper? I suggest you always do that, because as of the end of today, when you finish listening to me and to my colleagues, you'll feel confident about even taking on a scientific paper and raising the relevant questions with either the authors or others. So, just quickly go through the anatomy of a typical scientific paper. So, the title is a description of the subject of the paper, obviously, but as we've said, you can get these titles like X is associated with Y. Whoa, you think, scientists from Harvard Medical School, well, yeah, that's it, that's what they're saying. Well, we've seen that you can't, even right from the very first line of the paper, things can start to go wrong. So we need to be aware that the title may not actually be fully justified by what follows. That remind you of anything? Like a tabloid headline, for example? Same thing. Abstracts. A summary of what they did and what they found. Oh, that's great then. We don't have to read this 30-page perishing paper. We just read the abstract. Great. No. Abstracts have been analysed and compared with the actual contents of the paper. And I forget the percentage now. My friend and colleague Doug Altman at Oxford University will shoot me for not remembering, but he and his colleagues have trawled through hundreds and hundreds of papers comparing what was claimed in the abstract with what was actually substantiated in the paper. And it's not 100% the same. I forget what the failure rate is, but it is shocking. So you cannot just trust the abstract. The introduction, very useful to journalists or to anyone getting their head around it, because it shows you why they've done the paper, gives you a bit of background. And it will have references. You can look those up on the websites that we'll talk about shortly. Gives you, those explanatory paragraphs. Really helpful. Methods. As we've seen, very important, but, oops, sorry, won't come up. How the question was investigated, talks about the type of study, the results, all the stuff that is just quite technical, and then the discussion, which is really important because it often shows you where the weak points in the research actually are, because the referees will come back and say, well, what about this, what about that? And then when they send the paper back to the authors then fix it, try and get rid of the referees off their back by addressing these points, by explicitly stating what the weaknesses are. Incredibly helpful section. Also, sometimes addresses the issue of plausibility, which, as we've seen, is pretty crucial. So, references at the end, always useful. And that final line, often squeezed between the names of the at the end of the paper and the references, but very important, conflict of interest statement. Have a read of that after you've read the title. Might save you a lot of time. Okay, so the questions you need to answer here are, guess what? Exactly the same. So that's handy. So what we've just learned, we can apply to a full-blown scientific paper. So the who is, again, credibility, the authors and the institution, where, journal and impact factor, why, the feel of the subject matter, whether there's a conflict of interest, the how is the type of study, size of study, and then the what, questions of size of effect, p-values, plausibility. Now, because we've got a scientific paper now, we can drill down on these questions a bit more thoroughly. So let's do that. Let's look at that first one. So the first thing we can do is to check out the credibility of the authors and the institution. We can do that by looking at what they've done before, see if they've got a track record on this. So PubMed incredibly useful port of call because it contains, you just type in pubmed.gov, just PubMed will do it. You get to this screen, and then, for example, you're interested in what Wakefield or anybody else has done on MMR and autism, or autistic spectrum disorder, all those things. That's why the asterisk is there, because it's a wild card, and you can play around with it. You can find out what's already known, what this person has, what their track record is in this. Very useful website, free. And quite often, I'd say about 30% of the time, you can actually get access to the paper itself by clicking through. A lot of them are still behind paywalls. That's changing a bit. And you can always contact the researcher themselves to get them to email over the paper itself. So having dealt with that, the why. So we check for the conflict of interest statement. Very important. How? Now this relates to this issue that we've touched on several times, and now we're going to drill down in a bit more detail. The type of study. Now there is a pecking order of stories, of studies, and the lowest form of evidential weight is provided by some bloke you met in a pub, or a scientist you met at a conference, or a conference abstract. Because basically it's not been through even a semblance of refereeing. Sometimes conference abstracts are refereed, but they're given, because they want the money from the delegate, they're given a pretty cursory check over. So anecdote, conference abstracts, not compelling. Slightly better is the case series. Wakefield et al. Is a case series where you have, well, we've noticed these particular cases come through. We think there might be something going on. Back when I was a baby, back in the late 50s, there was an Australian doctor who came up with a case series, thought this is odd. I'm seeing a lot of babies appearing with deformed limbs. A very rare medical condition called phocomelia. And he thought, well, this is odd because this is really rare. I'm going to report this. And of course, that was the first signs of thalidomide, the thalidomide disaster, which presumably you all know about. So they do have their place, but they have to be treated with caution. Similarly, animal studies. Now, I don't know what you think about the concept of reincarnation, but if there is anything in it, I suggest you come back as a mouse, because they've been cured of everything. If you read the literature, the number of genetically based therapies, organ transplants, all sorts of stem cell things, they have been treated and cured of everything. But there is growing skepticism, vocal skepticism, not just from animal rights nutcases, but actually from serious academics who are saying, you know what, animals not really quite the same as humans. I think we need to be a bit more careful on this. And so you'll see a lot of papers now say, obviously this needs to be replicated in human trials. Whereas in the old days, there was a bit more excitement about animal studies than there is now. I'm not saying they never work. Obviously, for things like surgical techniques, they can be extremely suggestive of a successful technique. But for things to do with genes and stuff like that, not so much. Going up the pecking order, case control studies. Now, these are often used in epidemiology for tracking down links between something nasty and something in, like the environment, for example, or some widely practiced behaviour. So, classic example of a case control study is the Dolan Bradford Hills studies in the 50s and 60s and onwards from there of smoking and doctors. And what they did basically is a case control study is not, it doesn't have any random element to it. What you do is you get a whole load of people who've suffered from the thing you're concerned about, and you try and match each of the people in that group with a similar sort of type of person, and then you see are these people much more likely to get this? And from that you can sort of at least put a pointer towards, there might be some link here, but they are very subject to things you haven't taken into account, biases, confounding effects, but they do have their value, and sometimes they are the only way of sorting something out. Anybody remember the stories that rattled on until relatively recently of cancer, brain cancer and mobile phones? So again, ideally you'd like to get a random group of people, say you're never going to use a mobile phone for the next 20 years. Okay, so that's you out of it. Yeah, carry on. Okay. And we'll do that randomly, okay, and we can do the comparison. That's great. That's not going to be very acceptable. Similarly, the link between cancer and living near overhead power lines. We can't say, okay, all you lot, right, you're going to have to live under pylons. Yeah, 20 years, sorry about that. All in the name of science. You lot, yeah, go and live anywhere. All right? It's never going to happen. So it's not ideal as a form of research, but sometimes it's the only thing that's ethically possible. And sometimes it reveals really important things, as it did in the case of smoking. Then going up, observation and cohort studies. This is where you recruit, like the Million Woman study that's been running for many years, set up to look at 1 million women, not randomised, just 1 million women, and we try and know as much as we can about them, and then see what happens to them, and then see by sorting through the 1 million women if we can find any potential links between one thing and another. Again, there's a bit of an issue there because of the problem with randomisation, bias, confounders, things like that. But again, it's better than nothing at all. Then moving up, we have the randomised controlled trial. Now we're getting closer to the gold standard, which is where you take two groups of people. You give one the standard treatment for this particular disorder, and you give the other group, chosen completely at random, the homeopathic remedy, for example. And then you compare them. And because you've randomised, there's no reason for thinking you've got more people who are somehow particularly receptive to this particular drug in one cohort than the other. So the effects cancel out between the two groups. So that can be pretty good. But there's still a problem of blinding, that patients, if they know what they're getting, doctors, if they know what they're giving, can maybe treat the patients who are getting the homeopathic remedy a bit nicer because they're like that and think, yeah, we want homeopathy to really work here. And then the best evidence of all is a systematic review of blinded randomised controlled trials. That is where you pull together all of them, all of these top quality randomised controlled trials to find out what happened. That is the most compelling form of evidence and is incredibly powerful. So the next thing we need to look at is statistical power. So this speaks to the bigger problem of the two ways that studies can mislead us. The first one is the false positive, where they claim to have found things that don't exist. So we look for something scientifically and we found something. And the other one, of course, is the flip side of that, where we're misled because they did look for something and failed to find it, even though it does exist. So let's have a look at those two basic problems. The first one is where we find effects that don't exist, the false positive. This speaks to this problem of the replication crisis in science at the moment, which is people have looked for all sorts of stuff and they found it. So amongst the many culprits of this, one of the problems is many of these studies are quite small, and as a result, they can be prone to noise from all sorts of sources. Random noise. It could be that you've just happened to have picked a small group that just happens, by just bad luck, to suffer from this particular problem more than others. And another one is the standard way of controlling for the effect of randomness, which is this concept called statistical significance, is an incredibly feeble standard. It's the threshold that's typically needed to get your research into a refereed journal, but it is not very impressive. So I want to sensitize you to this because it's being recognized as a major problem. So the first big problem with p-values that trips up even scientists is that they're very confusing. Would anybody care to give me a definition of a p-value? A lot of statisticians suddenly go amazingly silent at this point. Okay, anybody? Right, a p-value is the probability of getting at least as impressive a result as that which you found if random chance were the real cause. So it's a calculation made on the assumption that random chance was actually to blame, responsible for what you saw. Okay. Now, you will see from that if you've done a calculation that puts a figure on that, you can't then flip it around, ignore the assumption and say, oh, so the probability that it's not random chance must be 95%. Because you can't use the same calculation to then throw aside the assumption on which the calculation was based. So a lot of even academics, you'll hear them say, well, the p-value was like 0.01, so it's only 1 in 100 chance that it's actually a fluke result. You can't do that. All you can say is, if this was the result of a fluke, then we'd only see this in 1 in 100 times. But that doesn't mean that there's only 1 in 100 probability that it really was a fluke. To actually do that calculation, which is the answer to the question you're actually interested in, requires an entirely different type of statistical calculation involving something called Bayesian inference, Bayesian methods, okay, which you don't even get taught, in all statistics courses until graduate level. So the other thing is, it's been shown that this standard of probability of getting this result or better by chance is less than 1 in 20, 0.05%, is a very feeble weight of evidence, especially if the claim being made is inherently pretty implausible. You can use Bayesian techniques to factor in plausibility with a p-value of 0.05, and typically what you find is on the order of like a quarter at least of results that would pass that 1 in 20 test are probably flukes. Suddenly it becomes a bit clearer why we're getting so many false positives in the literature. You can't trust what a lot of scientists will tell you about what they claim to have found. So I heard people talking about the discovery of the Higgs boson, where they described it in terms of a Six Sigma discovery, which is equivalent to an incredibly low p-value. And therefore they said there's only 1 in a million, or whatever it is, I forget what Six Sigma is, it's about 1 in a million, chance of it being a fluke result. No, that's not how it works. And these were people in charge of understanding the discovery of the Higgs. It has to be said that the Higgs is an inherently quite plausible hypothesis, and so there are all sorts of other reasons for believing they have found it. But that interpretation isn't right. And you can see symptoms of scientists who don't understand p-values when they say, well, so the probability of it being a fluke result is 1 in 20. Or in the paper, you will see p less than 0.032. That statement, for reasons I won't bore you with, makes no sense at all. It has to be an equal sign. It only makes sense for less than for certain values of p-values. When you see less than some weird number like that, it means the people who've written it don't actually know what they're doing. Many medical journals have really more or less insisted now that papers explain their results in terms of what are called confidence, 95% confidence intervals. That is also a bit misleading as a concept, but not quite as misleading by quite a long chalk as p-values. And so you will see this, which is the central value. So say this is a risk of getting cancer as a result of being exposed to this environmental carcinogen. That means 2.5 times greater risk. Whoa, that's really impressive. And then the 95%, there's a 95% interval within which this, the true figure is expected to lie under certain assumptions. And because this is slightly greater than 1, which means there's no increase in risk, it's statistically significant. So people typically look at that, whoa, big effect, and that, oh yeah, it's greater than 1, therefore it's statistically significant. Right, that's it, fine, we're done. In fact, there's another figure in there. And can you see that these two figures are quite, 1 is quite a big ratio of the other. It's about 6 times greater. What that's telling you is there's quite a wide confidence interval, right? And that means the weight of evidence is pretty feeble, probably because they haven't used many people. So don't make the mistake of many people, which is focusing on the central value and whether it's statistically significant. Use all the information. So if this is really wide, they really haven't made a very compelling case at all. And there are quantitative ways which I've developed and published papers on for converting that into what you should really think about a paper. Ooh. So the other way it can mislead, of course, is through effects that do exist, but it doesn't detect them. So we looked and we found nothing. And this speaks to the concept of statistical power and having an underpowered study. I crossed swords with an academic, Edzard Ernst, in the Journal of the Royal Society of Medicine some years ago, because he has done a lot of studies of homeopathic remedies and shown that there's nothing in them. They have no effect. And if you look at a lot of them, they are so small, they would struggle to detect the efficacy of aspirin, which actually does work every now and again. So if you don't want to find something, you can always come up with a small enough study that gets past the referees but fails to, comes up with the right result. Now, we agreed to differ on this, and he said that, some of the studies that he'd done were a tad on the underpowered side. So you have to look out for that, because that can be one of the reasons they failed to find things. As we've talked about a few times today, even big studies can be underpowered, because by the time they've sliced and diced them, you can have I came across a European study of cancer effects, and it has 500,000 being studied. Some of the claims are based on just a few hundred. Suddenly gone from 500,000 down to a few hundred. Got to look out for that, slicing and dicing effects. And they can, and studies can suffer from inherent biases, especially if they're case control studies, things like that. Plausibility is best checked by that most compelling form of evidence, the systematic review of randomised, double-blinded, randomised controlled trials. And the Cochrane collaboration is the go-to place for that. You just type in systematic review, Cochrane, and then whatever it is you're interested in, and they will give you the latest information. My 80-year-old mum has just had a hip replacement operation, and she is complaining all the time about the compression stocking she has to wear because the doctors told her to. And I wanted to know what the evidence for her suffering, whether it was actually worthwhile is. Went straight onto this, and yes, it is worth having to prevent deep vein thrombosis, even if you are taking drugs to prevent deep vein thrombosis. So I told my mum, sorry, you're going to have to put up with it. So again, you would do this if you were suddenly asked to look at the MMR and autism link, and you could get the Cochrane's latest pulled together. They keep revising them, adding to them, with a few years in between each review. 139 studies now, pretty impressive. No credible evidence. So the final thing that very often trips journalists up is where they have been told by their news editor, got this story, write it up, get some reaction, can you? This has its problems. We've already seen the need to get reaction in sometimes because you don't actually believe the story. It'd be quite helpful if you got some other academic to say, this is a load of garbage, because you'd get the news editor off your back. So this is a problem, getting some reaction. So who do you go to? Well, one obvious person to go to is other researchers. Seems to make sense. You go and speak to the leading expert on this particular subject, or another leading expert on this particular subject. But the trouble is, they too can have agendas. So one of the biggest changes I've seen in 30 years reporting journalism is the way that speaking to an academic now, you no longer get the feeling you're getting a fair and balanced view of both sides of a debate. You sometimes feel you're being fed a particular line, either supporting this particular case, like that cutting down on salt really is going to save lives from heart attacks, or that you're being fed a line that, it's all hysterical nonsense by an academic. Anybody saw the Michael Mosley programme? He had, forget what it is, Trust Me, I'm a Doctor, I think it's called, something like that. And he goes to experts on both sides of the debate, and they both make compelling arguments for mutually opposed arguments. So you always have to bear in mind that scientists have agendas. You have a point.
Oh, well, I was just going to say, I recently did a story on solar and shale gas, and went to sort of experts that are middle on solar and then experts on shale gas, and then also an expert on comparison. And it was only when all three voices said the same things where I was like, okay, definitely that's much more exciting. Right. But, and obviously there were agendas.
Yeah, you can see it, can't you? You really see it, especially with controversial issues, but also with things you think were pretty okay, but everybody's scrabbling for fun, so you have to bear that in mind. The other ones you go to, of course, are NGOs, charities, research charities, and campaigners. Obvious in some cases that they have an agenda to push. I mean, Greenpeace and NGOs they do wonderful jobs in some way, but their business model relies on publicity. So they are going to talk stuff up. I don't blame them for that. That is the way that they do things. But one always has to bear that in mind. Cancer research, similarly. They are, like all these research charities, they want to strike that balance, which is difficult, between saying something positive but not giving false hope. So it's very difficult, but one has to be aware that these people all have agendas.